Hi. Hello everyone. Welcome to information sharing session on failure analysis. In previous session, we discussed about forging process defects. Today, we will discuss about extrusion process defects. Extrusion is a fundamental manufacturing process that shapes materials into desired forms, often with high precision and efficiency. It involves forcing a material through a die opening, resulting in an object with a specific cross-sectional profile. The basic mechanics of an extrusion process. Step 1. Material preparation. Solid materials. Metals, for example, are formed into billets before heating them to a plastic state. Plastics and polymers, pellets are melted and homogenized to ensure consistent flow. Step 2. Die placement. The die is a crucial component, fabricated with a specific internal geometry that dictates the final shape of the extrudate. It is securely mounted in the extrusion equipment. Step 3. Pressure application. Depending on the type of extrusion, pressure is applied to the material through different mechanisms. Direct extrusion, a rem directly pushes the material through the die. Indirect extrusion, a rem compresses a container holding the material, forcing it through the die. Screw extrusion, a rotating screw conveys and compresses the material towards the die. Step 4. Material flow and shaping. Under high pressure, the material flows plastically through the die opening, conforming to its shape and dimensions. This creates the desired cross-sectional profile of the extrudate. Step 5. Cooling and solidification. The extrudate exits the die and cools rapidly, solidifying into the final product. Let us understand types of extrusion processes. Hot versus cold extrusion. Hot extrusion. Performed at high temperatures for metals and some plastics, enabling easier flow and reduced pressure requirements. Cold extrusion. Usually reserved for softer materials like aluminium and copper, offering advantages like high strength and better surface finish. Direct versus indirect extrusion. Direct extrusion. Simple and efficient, suitable for basic shapes and high production rates. Indirect extrusion. Offers better control over material flow and pressure, ideal for complex shapes and hollow sections. Other types. Blown film extrusion. Creates thin plastic film by inflating the extrudate with air. Co-extrusion. Combines multiple materials through separate die channels to create layered structures. Applications of extrusion. Extrusion has a vast range of applications across various industries, including construction, metal beams, pipes, window frames, and architectural profiles. Automotive. Engine parts, body panels, bumpers, and interior components. Packaging. Bottles, tubes, film, and food containers. Medical. Syringes, catheters, tubing, and prosthetics. Consumer products. Pens, toys, furniture components, and electronic casings. Advantages of extrusion. High production rates. Capable of producing large quantities of consistent quality products. Versatility. Handles various materials and creates complex shapes with high precision. Efficient material utilization. Minimizes waste and optimizes material consumption. Cost-effective. Offers a relatively inexpensive manufacturing process for high-volume production. Disadvantages of extrusion. Limited to shapes defined by the die. New shapes require additional die fabrication. High initial investment. Equipment and tooling costs can be substantial. Potential material degradation. High temperatures and pressures may affect certain materials. Conclusion. Extrusion is a powerful and versatile manufacturing process, widely used for shaping various materials into desired forms. By understanding the basic mechanics, different types, and applications, one can appreciate the significant role extrusion plays in producing a vast range of products we encounter daily. Common types of defects observed in extrusion. Surface defects. Die lines. Hairline marks on the surface caused by uneven flow through the die. Scoring. Scratches or gouges on the surface, often due to die wear or contaminants. Pickup. Material adhering to the die surface and transferring to the extrudate. Tearing. Irregular surface breaks caused by improper die design or process parameters. Porosity. Small holes or voids on the surface, resulting from trapped air or moisture. Weld lines. Visible lines where two streams of material meet, often seen in co-extrusion. Dimensional defects. Dimensional inconsistency. Variations in length, diameter, or other dimensions beyond acceptable limits. Warpage. Distortion of the extrudate cross-section due to uneven cooling or stress. Twisting. Undesirable twisting or rotation of the extrudate along its length. Swelling. Enlargement of the extrudate beyond the die dimensions due to material properties or process issues. Internal defects. Voids. Internal cavities or air pockets within the extrudate, affecting its strength and integrity. Intrusions. Foreign particles trapped inside the extrudate, compromising material properties. Degradation. Chemical or structural changes within the material due to excessive heat or pressure. Cracks. Internal fractures in the extrudate, often caused by stress or material defects. Flow-related defects. Surging. Irregular flow of material through the die, resulting in inconsistent dimensions and surface quality. Roping. Formation of rope-like strands within the extrudate due to improper mixing or temperature control. Fish eyes. Surface defects caused by air bubbles trapped in the material. Other defects. Color inconsistencies. Variations in color or shade across the extrudate. Poor surface finish. Rough or uneven surface texture, affecting the aesthetics and functionality. Mechanical property variations. Deviations in strength, stiffness, or other mechanical properties. This list is not exhaustive, and the specific types of defects observed will depend on the material being extruded, the process parameters, and the specific application. Now, we will take deep dive into each defect mentioned here. Die lines in extrusion, a closer look. Die lines are a common surface defect observed in extruded products, appearing as hairline marks or ridges running along the length of the extrudate. These lines can detract from the aesthetics and, in some cases, affect the functionality of the product. Understanding the causes and solutions for die lines is crucial for improving product quality in extrusion processes. Causes of die lines. Several factors can contribute to the formation of die lines. Die surface imperfections. Roughness, scratches, or other imperfections on the die land can cause uneven flow of the material, leading to die lines. Material properties. Certain materials are more prone to die lines due to their viscosity, flow behavior, and sensitivity to temperature. Process parameters. Improper temperature, pressure, or flow rate can lead to variations in material flow and die line formation. Contamination. Foreign particles in the material or die can cause uneven flow and lead to die lines. Die wear. Over time, the die's surface can wear, creating irregularities that contribute to die lines. Poor die design. Improper die geometry or flow channels can result in uneven pressure distribution and die line formation. Consequences of die lines. The impact of die lines depends on the severity and application of the extruded product. Some potential consequences include reduced aesthetic appeal. Die lines can detract from the appearance of the product, especially for applications requiring a smooth finish. Impaired functionality. In some cases, die lines can affect the mechanical properties, wear resistance, or other functional aspects of the extrudate. Production delays. Identifying and correcting die line issues can lead to production downtime and increased costs. Minimizing die lines. Several strategies can be employed to minimize the occurrence of die lines. Maintaining a smooth die surface. Regularly cleaning and polishing the die land is crucial to prevent imperfections and ensure consistent material flow. Optimizing process parameters. Fine-tuning temperature, pressure, and flow rate can significantly impact die line formation. Utilizing high-quality materials. Selecting materials with appropriate flow properties and minimizing contamination risks can help reduce die lines. Implementing proper die design. Employing advanced die design techniques and incorporating flow simulation can create consistent material flow and minimize die line formation. Regular die maintenance. Scheduling routine die maintenance and inspections can detect and address wear issues before they significantly impact product quality. By understanding the causes and consequences of die lines and implementing effective preventive measures, manufacturers can ensure high-quality extruded products with optimal surface finish and functionality. Scoring in extrusion. Understanding the problem. Scoring refers to the presence of scratches or gouges on the surface of an extruded product. Unlike die lines, which are often faint and hairline thin, scoring presents as more pronounced and visible defects. These marks can significantly detract from the product's aesthetics and, in severe cases, compromise its functionality and performance. Causes of scoring. Several factors can contribute to the formation of scoring in extrusion. Die wear. As the die undergoes repeated use, its land surface can wear unevenly, leading to sharp edges or protrusions that scratch the extrudate. Contamination. Foreign particles present in the material or die can act as abrasives, causing scratches and scoring on the extrudate surface. Improper die design. Die channels with sharp corners, abrupt transitions, or inadequate lubrication provisions can promote scoring. Excessive pressure. High pressure applied during extrusion can force the material against the die land with greater force, exacerbating scoring issues. Material properties. Materials with high abrasive content or poor flow properties can be more susceptible to scoring. Improper handling. Rough handling of the extrudate after exiting the die can also cause scoring. Consequences of scoring. The severity of the scoring defect influences its impact on the product. Reduced aesthetic appeal. Scoring can significantly impact the product's appearance, making it less visually appealing and commercially undesirable. Functional issues. Depending on the depth and location of the scoring, it can weaken the product's structural integrity, impact its wear resistance, and affect its performance in specific applications. Production delays. Identifying and addressing scoring issues can lead to production downtime and increased costs. Preventing and mitigating scoring. Several strategies can be implemented to minimize the occurrence of scoring. Regular die maintenance. Regularly cleaning, polishing, and inspecting the die land helps prevent wear and ensures a smooth surface for material flow. Controlling process parameters. Optimizing pressure, temperature, and flow rate can reduce the risk of scoring by minimizing stress on the die and material. Utilizing proper die design. Employing advanced die design techniques with smooth transitions, rounded corners, and appropriate lubrication channels can significantly reduce scoring. Filtering the material. Implementing filtration systems to remove foreign particles from the material before extrusion can prevent them from acting as abrasives and causing scratches. Handling the extrudate with care. Implementing proper handling procedures and equipment to minimize contact and friction between the extrudate and other surfaces can prevent post-extrusion scoring. Selecting appropriate materials. Choosing materials with suitable flow properties and minimal abrasive content can help reduce the likelihood of scoring. By understanding the causes and consequences of scoring and implementing effective preventive measures, manufacturers can ensure high-quality extruded products with a smooth, aesthetically pleasing, and functional surface finish. Pickup in extrusion. Understanding the defect. Pickup is a common surface defect observed in extrusion processes, appearing as small, irregular deposits of material adhered to the surface of the extrudate. These deposits can vary in size and shape, ranging from fine specks to larger, elongated patches. Pickup can significantly affect the product's aesthetics and, in some cases, compromise its functionality. Causes of pickup. Several factors can contribute to the formation of pickup during extrusion. Material properties. High viscosity. Materials with high viscosity tend to adhere more readily to the die surface, increasing the risk of pickup. Low melting point. Materials with low melting points can partially melt and stick to the die land, contributing to pickup formation. Presence of oxides or other contaminants. Oxides and other contaminants on the material surface can act as bonding agents, facilitating adhesion to the die. Process parameters. High pressure. Excessive pressure during extrusion can force the material against the die land with greater force, increasing the likelihood of pickup. Uneven flow. Inconsistent flow of material through the die can lead to localized areas of high pressure and increased pickup formation. Improper lubrication. Insufficient or inadequate lubrication can cause friction between the material and the die, leading to pickup. Die wear and contamination. Rough die surface. Wear and tear on the die land can create irregularities that trap material and contribute to pickup formation. Die contamination. Foreign particles present on the die surface can act as bonding sites for the material, leading to pickup. Other factors. Improper die design. Die channels with sharp corners or abrupt transitions can create localized areas of high pressure and increased pickup. Extrusion speed. High extrusion speeds can exacerbate existing pickup issues due to increased shear forces and reduced contact time for lubrication to be effective. Consequences of pickup. The severity of pickup can significantly impact the quality and functionality of the extruded product. Reduced aesthetic appeal. Pickup can detract significantly from the product's appearance, making it less visually appealing and commercially undesirable. Functional issues. In severe cases, pickup can affect the product's dimensional accuracy, surface finish, and even its mechanical properties. Production delays. Identifying and removing pickup can lead to production downtime and increased labor costs. Material waste. Removing pickup often involves additional processing steps, leading to material waste and reduced production efficiency. Preventing and mitigating pickup. Several strategies can be employed to minimize the occurrence of pickup. Optimizing process parameters. Fine-tuning pressure, temperature, and flow rate can significantly impact pickup formation by reducing localized areas of high pressure and promoting even material flow. Proper lubrication. Utilizing appropriate lubricants and ensuring consistent application across the die land can effectively reduce friction and prevent material from sticking to the die surface. Regular die maintenance. Regularly cleaning and polishing the die land helps prevent wear and ensures a smooth surface for material flow, reducing the risk of pickup. Controlling material properties. Selecting materials with suitable viscosity, melting point, and minimal contaminants can inherently reduce the likelihood of pickup. Implementing proper die design. Employing advanced die design techniques with smooth transitions, rounded corners, and appropriate lubrication channels can significantly reduce pickup. Optimizing extrusion speed. Adjusting the extrusion speed to minimize shear forces and provide sufficient time for effective lubrication can help prevent pickup formation. Utilizing online monitoring systems. Implementing real-time monitoring systems to detect pickup occurrences can facilitate prompt corrective actions and minimize the impact of the defect. By understanding the causes and consequences of pickup and implementing effective preventive measures, manufacturers can ensure high-quality extruded products with a clean, smooth, and aesthetically pleasing surface finish. Tearing in extrusion. Understanding the defect. Tearing is a surface defect that manifests as irregular breaks or cracks in the extruded product. These tears can vary in size and severity, ranging from hairline cracks to deep lacerations that compromise the entire cross-section of the extrudate. Tearing can significantly impact the product's aesthetics, functionality, and overall quality. Causes of tearing. Several factors can contribute to the formation of tearing during extrusion. Material properties. Low ductility. Materials with low ductility have limited ability to deform plastically, making them more prone to tearing under stress. Internal stress. Internal stresses trapped within the material due to uneven heating or cooling can lead to spontaneous tearing during extrusion. Presence of intrusions or voids. Intrusions such as oxides or other foreign particles within the material can act as stress concentrators, increasing the risk of tearing. Process parameters. Excessive pressure. Applying too much pressure during extrusion can exceed the material's strength and lead to tearing. Uneven flow. Inconsistent flow of material through the die can create localized areas of high stress and initiate tearing. Improper die design. Sharp corners, abrupt transitions, or insufficient vent channels within the die can create stress points in the material, leading to tearing. Incorrect temperature. Excessively high or low temperatures can negatively impact the material's flow properties and ductility, increasing the risk of tearing. Other factors. Die wear. Worn or damaged die land can cause the material to flow unevenly, leading to localized areas of high stress and tearing. Improper handling. Rough handling of the extrudate after exiting the die can lead to tears and other surface defects. Consequences of tearing. The severity of tearing can have significant consequences for the extruded product. Reduced aesthetic appeal. Tearing significantly detracts from the product's appearance, making it commercially undesirable and unsuitable for certain applications. Functional issues. Depending on the location and severity of the tear, it can compromise the product's structural integrity, leading to performance failures and safety concerns. Material waste. Extruded products with severe tearing are often deemed unusable and discarded, resulting in material waste and reduced production efficiency. Production delays. Identifying, analyzing, and correcting the root cause of tearing can lead to production downtime and increased costs. Preventing and mitigating tearing. Several strategies can be employed to minimize the occurrence of tearing. Optimizing process parameters. Fine-tuning pressure, temperature, and flow rate can significantly impact tearing by reducing stress on the material and ensuring consistent flow through the die. Selecting appropriate materials. Utilizing materials with good ductility and minimal internal defects can inherently reduce the risk of tearing during extrusion. Implementing proper die design. Employing advanced die design techniques with smooth transitions, rounded corners, and appropriate vent channels helps distribute stress evenly and prevent localized areas of high strain. Utilizing proper lubrication. Applying appropriate lubricants to the die land and material can reduce friction, improve flow, and minimize stress on the material, thereby preventing tearing. Controlling die wear and contamination. Regular maintenance and cleaning of the die land can prevent wear and ensure a smooth surface for optimal material flow, reducing the risk of tearing. Monitoring and controlling material properties. Implementing quality control measures to ensure consistent material properties and identify potential defects before extrusion can prevent tearing occurrences. Optimizing handling procedures. Implementing proper handling procedures and equipment throughout the extrusion process can minimize the risk of damage and tearing to the extrudate. By understanding the causes and consequences of tearing and implementing effective preventive measures, manufacturers can ensure high-quality extruded products with a smooth, defect-free surface and optimal functional properties. Porosity in extrusion. Understanding the hidden enemy. Porosity, the presence of small holes or voids within the extruded product, is a common and often insidious defect. Unlike surface defects like scratches or cracks, porosity can be hidden beneath the surface, making it difficult to detect and potentially compromising the product's functionality and integrity. Causes of porosity. Several factors can contribute to the formation of porosity during extrusion. Material properties. High moisture content. Excess moisture trapped in the material can vaporize during extrusion, leaving behind voids and compromising the final product. Gases. Air trapped within the material or introduced during processing can expand and create voids within the extrudate. Shrinkage. Uneven shrinkage of the material during cooling can lead to internal voids and surface imperfections. Process parameters. Improper temperature control. Excessive or insufficient heat can affect the material's flow and gas solubility, leading to porosity formation. Incorrect pressure. High pressure can trap air within the material, while low pressure may not be sufficient for proper densification, resulting in voids. Rapid cooling. Rapid cooling can trap gases and prevent proper material flow, leading to internal porosity. Die design and maintenance. Improper die design. Die channels with insufficient venting can trap air and contribute to porosity. Die wear and contamination. Worn or contaminated die land can lead to uneven flow and gas entrapment, resulting in porosity. Other factors. Material handling. Improper handling of the material before or after extrusion can introduce air or damage the material, leading to porosity. Lubrication. Insufficient or inappropriate lubrication can increase friction and affect gas solubility, contributing to porosity formation. Consequences of porosity. The severity of porosity can significantly impact the extruded product. Reduced mechanical properties. Voids weaken the material, compromising its strength, stiffness, and fatigue resistance. Leakage and fluid infiltration. Porosity can allow liquids or gases to pass through the material, compromising its functionality and potentially leading to safety concerns. Reduced aesthetic appeal. In some cases, porosity can create visible surface imperfections, impacting the product's visual appeal. Increased production costs. Identifying, correcting, and discarding products with porosity can lead to production downtime, material waste, and increased costs. Preventing and mitigating porosity. Several strategies can be employed to minimize the occurrence of porosity. Controlling material properties. Pre-drying the material to remove moisture, selecting materials with low gas content, and optimizing the material's composition can significantly reduce porosity. Optimizing process parameters. Fine-tuning temperature, pressure, and cooling rate can ensure proper gas removal and densification of the material, minimizing porosity formation. Implementing proper die design and maintenance. Employing advanced die design techniques with adequate venting and ensuring regular die cleaning and maintenance can prevent air entrapment and porosity. Utilizing proper lubrication. Choosing appropriate lubricants and ensuring consistent application can reduce friction and promote even flow, minimizing gas entrapment and porosity. Implementing proper handling procedures. Careful handling of the material throughout the process can prevent air introduction and damage that could lead to porosity. Monitoring and controlling process parameters. Implementing real-time monitoring systems to track temperature, pressure, and other parameters can help identify and address issues that contribute to porosity before they occur. By understanding the causes and consequences of porosity and implementing effective preventive measures, manufacturers can ensure high-quality extruded products with optimal mechanical properties, functional performance, and aesthetic appeal. Remember, porosity can be a silent enemy, but by being vigilant and proactive, manufacturers can protect their products and ensure customer satisfaction. Weld lines in extrusion. Understanding the merging mark. Weld lines, also known as knit lines, are visible seams that appear on the surface of an extruded product. They occur when two streams of material rejoin within the die cavity, often during co-extrusion processes where different materials or colors are combined. While not inherently detrimental, weld lines can affect the product's aesthetics and, in some cases, its functionality. Formation of weld lines. Weld lines form when two separate streams of molten material flow together inside the die channel before solidifying into the final product. The specific factors influencing their formation include die design. The geometry of the die channels plays a crucial role. Narrow channels or abrupt transitions can hinder smooth merging, resulting in more pronounced weld lines. Material properties. The viscosity and flow characteristics of the materials being co-extruded can affect how readily they merge, impacting the visibility of the weld line. Process parameters. Temperature, pressure, and flow rate all influence the material flow and merging process. Deviation from optimal settings can exacerbate weld line formation. Material compatibility. Incompatible materials may not bond effectively, leading to weak weld lines and potential functional issues. Consequences of weld lines. While not always detrimental, weld lines can have various consequences depending on their severity and the application of the extruded product. Reduced aesthetic appeal. Visible weld lines can detract from the product's appearance, especially in applications requiring a smooth, uniform finish. Compromised functionality. In critical applications, weak or porous weld lines can affect the product's strength, structural integrity, or resistance to fluids or gases. Material waste. Products with severe weld lines may be deemed unusable and discarded, leading to material waste and production inefficiencies. Minimizing weld lines. Several strategies can be employed to minimize the formation and impact of weld lines. Optimizing die design. Employing advanced die design techniques with smooth transitions and appropriate channel geometries can promote smooth merging and reduce weld line visibility. Selecting compatible materials. Choosing materials with similar flow properties and good compatibility can enhance merging and minimize weld line formation. Fine-tuning process parameters. Adjusting temperature, pressure, and flow rate within optimal ranges can ensure smooth material flow and promote effective merging, minimizing weld lines. Utilizing flow simulation software. Employing simulation tools can help predict material flow behavior within the die and optimize the design for minimal weld line formation. Implementing post-processing techniques. In some cases, techniques like polishing or surface finishing can improve the appearance of the weld lines, making them less noticeable. By understanding the formation, consequences, and mitigation strategies for weld lines, manufacturers can produce high-quality extruded products with improved aesthetics, functionality, and overall value. Remember, a little attention to detail in the extrusion process can go a long way in ensuring a seamless and satisfying end product. In next session, we will go through few more extrusion process defects in detail. Thank you.